Hello friends, welcome to engineering tutorial. So we'll continue our discussion on thermodynamics with the discussion which we are having on thermal properties of matter, that is solid, liquid and gases. So in this video we are going to discuss, in a very quick and short manner, we'll discuss the ideal gas equation. Why? Because in detail we'll have this discussion in kinetic theory of gases. We'll discuss that, we'll discuss it in detail, a lot of aspects, a lot of concepts involved in it. But here, why I'm introducing this right now, because in our upcoming discussions related to thermal properties of matter, this ideal gas equation will come into play. So just have a good idea, a basic idea of what it is. In detail, we'll discuss it in kinetic theory of gases. Okay. So ideal gas equation. So in this we have this ideal gas thing. When we discussed gas laws, that is Boyle's law, Charles' law and Gay-Lussac's law, there also this concept of ideal gas, it came into play. About it, like I said, we'll discuss in kinetic theory of gases, but just have a basic idea of what ideal gas and real gas, what these two, they mean. So basically, an ideal gas is a hypothetical concept. Okay, this is how all gases should behave ideally, hypothetically. So at any condition of temperature and pressure, the ideal gas, what the ideal gas concept, it basically tries to say that all gases, they should behave in a similar manner at all conditions of temperature and pressure. That is the concept of ideal gas. But real gases, they do not behave in that way. They have different behavior, and at different temperature and pressure combinations, they behave in a different manner, which is very different from the concept of ideal gas. So all the gases which are present in the environment, they are real gases. But we need, for reference, for a comparison, to measure the deviation in behavior of real gases from the idealized concept, we need the concept of ideal gases. So the laws, Boyle's law, Charles' law, Gay-Lussac's law, they are generally, applicable, they are applicable for real gases for comparison, for reference, but they take into consideration this hypothetical concept of ideal gas. Okay, and another important thing, these real gases, they come very close to the the ideal curve under certain conditions of temperature and pressure combination, which is basically high temperature and low pressure. But at normal temperature and pressure, they behave in a very random manner. They exhibit different behavior at different temperature and pressure, which is not close to ideal gas behavior. Okay, so this is ideal and real gases. Now, I also, during our discussion on the gas laws, we touched this part that in order to specify any thermodynamic system, be it solid, liquid or gas, especially for gases, for behavior of gases, but for any system, any thermodynamic system, three important parameters are very important, which are called as thermodynamic variables or thermodynamic parameters. They are pressure, temperature and volume. So every thermodynamic relationship, it will be either it will involve either one or all of these thermodynamic parameters. Okay, so every equation that you will see in thermodynamics while studying thermodynamics, it will either involve pressure, temperature, volume, any two of them or all of them. So in this ideal gas equation, which we will discuss right now, it will involve the three of them. Okay, that is pressure, volume and temperature. So here we'll just have a quick recap of the gas laws, because we will be deriving the perfect gas equation from the gas laws. So we have already discussed Boyle's law, Charles' law and Gay-Lussac's law. So we'll just quickly see it. So Boyle's law, it's a fundamental gas law which gives the relationship between volume and pressure. So Boyle's law states that volume is inversely proportional to pressure. Okay, I'm not going any further, just the gist of the law, and that we'll discuss. Volume is inversely proportional to pressure. That is Boyle's law. Okay, and this is the curve between pressure and volume, and this is for the reciprocal of volume and pressure. Then Charles' law. So Charles' law, it gives the relationship between volume and temperature of a gas at constant pressure. So essentially, Charles' law states that when pressure is remaining constant, the volume of a given mass of gas is directly proportional to its absolute temperature. Okay, so when it is expressed in Kelvin. Okay, this. Then, so here in Boyle's law, here it is at constant temperature. Temperature remaining constant, volume is inversely proportional to pressure. In Charles' law, pressure remaining constant, volume is directly proportional to temperature. Okay, and this is the graph, okay, volume and temperature, which is expressed in Kelvin. Then we have Gay-Lussac's law. So this gives the relationship between pressure and temperature at constant volume. So here, basically, at constant volume, the pressure of a given mass of gas is directly proportional to its absolute temperature. Again, measured in Kelvin. Okay, and this is the curve, pressure and temperature in Kelvin. So now, if we combine all these gas laws, if we take them together, okay, so let's say we take Charles' law, we can derive this equation by taking any two of them. Okay, so here let's say we take Charles' law, which states that volume is directly proportional to temperature. So here volume is one thermodynamic variable, temperature is another thermodynamic variable. That's Charles' law. Then we have pressure is directly proportional to temperature. That is Gay-Lussac's law. So we can say that pressure and volume, both of them which are directly proportional to temperature, we can say PV is directly proportional to T, that is pressure and volume, the product of pressure and volume, that is directly proportional to temperature. So now we have to introduce a proportionality constant, okay, that is PV is equal to RT, okay. So where R is called as the universal gas constant, and this is for 1 mole of a gas, okay, for 1 mole of a gas. PV is equal to RT. Now, if we want to write the equation for n moles of a gas, then that will be PV is equal to nRT, okay, where n is the number of moles of gas and R is called as the universal gas constant, which is 8.31 joule per mole per Kelvin. So here don't get confused by seeing these units and all that. Like I said, we'll be discussing it in detail in kinetic theory of gases. So as I'm going to discuss it in detail during that time, that's why I'm not unnecessarily extending this whole discussion, because just for reference we'll need in the upcoming discussions, this equation will come. So there you don't get confused how this equation came and all that. So here I've just given you a brief and basic idea. Okay, we'll discuss it in detail in kinetic theory of gases. So here this is the ideal gas equation. PV is equal to nRT. P is the pressure, V is volume, T is temperature, N is the number of moles of gas, and R is the universal gas constant. And this is called as the ideal gas law or ideal gas equation or the perfect gas equation, whatever you want to call it. Okay, so this is the ideal gas equation, which is derived from Boyle's law, Charles' law and Gay-Lussac's law. You can see everything is written here. Okay, if you want to write V, which is equal to nRT by P. Here you see, here volume is directly proportional to temperature and volume is inversely proportional to pressure, both the gas laws. Okay, so you can derive this equation by taking any two gas laws and combining them. Okay, so basically in essence it involves all three gas laws: Boyle's law, Charles' law and Gay-Lussac's law. Okay, so here, and as you can see here also pressure, we can write it as nRT by V. So here pressure is inversely proportional to volume, which is essentially the same thing, and pressure is directly proportional to temperature. And here V is equal to nRT by P. Here volume is directly proportional to temperature, like we have said. So it involves all the three gas laws. Just by picking any two we can derive it. Okay, so this is the ideal gas equation.